I'd like to preface my introduction to the next speaker by reminding many of you that last spring, a little bit more than a year ago, launch of a spacecraft called the Transient Exoplanet Survey Satellite took place. Some of you were there to actually see the launch. I was texting with Jackie Hewitt, who was largely responsible for managing the project at various stages, and about a minute before launch, she sent a text that said, "My stomach hurts." So anyway, I don't want to give too much of Stephen Villanueva's talk, but Tess is there, it is doing something, and Stephen Villanueva will tell us about it.
Thank you so much. Yes, Tess did launch. It survived. I was very thankful that it launched. The launch was scheduled after I'd already gotten the offer, so that if something did go wrong, I at least had a job. So yes, I'm going to be talking about the search for long-period giant planets in Tess, the Transient Exoplanet Survey Satellite. I'm very fortunate that I am a planet hunter. I look for planets around other stars, and in my obviously biased opinion, I just think it's the best job in the world. But thinking about giant planets, or just thinking about planets in general, let's just ask, first of all, you can ask the philosophical questions. Are we alone in the universe? Are there other Earths out there? Maybe if this one doesn't pan out. More scientifically, some questions that have been thought about and we've been trying to answer more recently. How common are other planets out there? What are planets made of? What are their compositions? What are their atmospheres? All interesting questions. But I think if you want to sort of think about these questions, you also need to think about, more importantly, how do planets form? And sort of maybe even beyond an individual planet, but how do solar systems form? How do planets as an ensemble form together? So I sort of want to focus on these two so that we can tie them back to just the general questions about exoplanets. So first off, how do solar systems form? All right, so here we have our own solar system, an amazing laboratory experiment. But how do we think it formed, at least back in the day when no one was around? Originally, we think that there was this giant cloud of gas. Most of it ended up in the sun. But around that giant cloud of gas was this disk, and the disk is made out of dust and debris and gas and all the things that eventually form the planets in our solar system. Over time, the rocky material accretes, forms these cores. They then accrete on gas, so on and so forth. And you build planets that mostly resemble the architecture in our solar system. It was the only data point we had, so all models had to fit this picture. The prevailing theory is that the radiation, basically the sunlight, pushed all the gassy material away from the inner solar system. This is why you have mostly rocky planets farther in. All of that gas ends up further out, and you have giant planets further out. Okay, makes sense. It fits our solar system. Over time, of course, this disk eventually dissipates, and you're left with the solar system as we see it today. All right, that's great. However, there was one class of planets, at least the class of planet that I studied as a graduate student, called a hot Jupiter. Now, in this scenario, you take this system, but imagine taking this giant planet Jupiter, but instead of having it where it is now, where it orbits its planet far, far out, or orbits the star much further out on orbital periods of years, and instead you're going to take it and you're going to shove it in 10 times closer to its host star than Mercury is to the sun, right? Take a giant planet and just shove it right next to the star. Now it's orbiting once every week or even less, right? This throws a major wrench into sort of all of the theories that we thought we had about how solar systems and how planets formed. And these are the class of planets that I studied as a graduate student, hot Jupiters. However, they sort of brought up more questions than they answered when we first started finding hot Jupiters. So, how do you form a giant planet so close to the star? Is it even possible? Most people don't think that is actually possible. So the real question is sort of, did you form it somewhere else and did it migrate in? And if so, what were the mechanisms that you actually can cause a giant planet to move that close in? And if so, what happens to all those other planets? What would happen to our own solar system, to our own Earth, had one of these giant hot Jupiters formed in our own solar system? Would we even be here? So these are some interesting questions. And it's sort of embarrassing that we've known about giant planets for about 25 years. The first ever exoplanet ever discovered was a hot Jupiter, one of these giant, close-in giant planets. And it was discovered way back in 1995. And since then, we still don't understand fully how to create a hot Jupiter and how it got there, right? This is still sort of an open-ended mystery in sort of planet formation or sort of exoplanet science in general. It's one of these big unanswered questions. And I'm hoping to sort of shed some light on that. So why don't we understand how hot Jupiters form? We find hot Jupiters, we're able to find them, but studying hot Jupiters doesn't really tell us about how they got there. And this is why. So we can think about two different theories for how to create a hot Jupiter. All right, theory A, we have our host star, and we have our planet, and it's sitting in that disk I was talking about. Now in this scenario, for whatever reason, the conditions are just right that you have this planet on some 1,000-day period, just like our own Jupiter. But during its formation, conditions in the disk are just right that as it's forming over time, there's actually a viscous drag present in the disk that causes the planet to slowly but surely spiral inward over time. Eventually, it's going to sort of shrink down to a shorter and shorter period and sit basically the inner edge of the disk and then stall. What you end up with then is this sort of giant planet on a very short period. Okay, that's one mechanism, at least possible mechanism. The other is what we call the high eccentricity migration mechanism. In this case, we have a giant planet forms in the disk, just like our own Jupiter. It's on this nice 1,000-day orbit. Everything is fine. It would be a normal solar system or a normal planet. But in this case, it has a buddy, either another star or another planet. And in this case, the two interact gravitationally, or they just get too close to one another. And the third body ends up being ejected from the system, while our giant planet ends up on a plunging orbit inwards towards the host star. Now this puts it on a highly eccentric orbit, and on every periastronic passage, there's an exchange of angular momentum between the star and the planet. This slowly shrinks the orbit and circularizes the orbit over time. So the end result is, again, a very short period giant planet. That's great. We have two possible mechanisms. This is a good place to start. But why is studying hot Jupiters now doesn't really tell us about which one of these sort of scenarios was plausible. And that's because the end result is the exact same, a very short period giant planet on a very circular orbit, right? It doesn't really tell us how they got there or which of these is sort of the dominant mechanism. So what you would like to do instead of looking for more short period giant planets that we have is look for maybe longer period or intermediate giant planets, because they would have the imprint of the original orbit still there. So if you could find maybe like a 30 or 100-day orbit giant planet, on one scenario you would find, if the disk migration theory was the prevailing one, you would find lots of giant planets on circular orbits at periods of about 100 days. And on the other scenario, you would find them mostly on eccentric orbits. So this is a testable theory, right? If you could find giant planets on these intermediate orbits, you could then measure their properties and then go out and sort of discern which one of these is correct. But unfortunately, we don't know of many giant planets on long period orbits. All of our sort of detection mechanisms are all biased towards short period planets. So we find lots of short period planets. We don't find very many long period planets. And when we do, they're usually around really faint stars, so we can't really measure their properties that well. So what I've been thinking about is sort of where can I find lots and lots of giant planets? You know, can I then measure their orbits and sort of can I discern which one of these theories is sort of the right one? So that's what I do. And right now, at least thus far, since I've been a Pappalardo Fellow, I've been focusing on this first question, which is sort of where can I find lots and lots of warm Jupiters? Luckily, so the mechanism, so briefly the method that I use to detect planets is the transiting method. So in this case, you monitor lots of stars, and hopefully, eventually, one of those planets will pass in front of its star. As it does, it blocks some of the starlight, giving you this characteristic dip, where the dip is sort of proportional to the size of the planet. So I try to measure three things about this light curve. This is what we call the light curve. But that's the depth. Sort of a larger planet will cast a larger shadow. That sort of makes sense. The duration, so how long, go back. How long the event lasts tells me something about how fast the planet is moving. That tells me something about its orbital properties. And then this sort of ingress and egress, these slanty bits, tell me something about the geometry. So this is what I do, is I look for planets that transit, that pass in front of their star, blocking some of their starlight. And this is a very subtle effect. It's only about a 1% dip for a giant planet. And then I try to measure the properties of the light curve. But to do that, I need to find these planets. But luckily here at MIT, you had the foresight to build me this amazing space telescope called Tess, the Transiting Exoplanet Survey Satellite, which has been monitoring essentially the entire sky looking for giant planets in a way that really hasn't been done before. So I want to show a quick movie that I borrowed from MIT's own George Ricker. So the Tess satellite, which was launched about a year ago, has been monitoring the entire sky, focusing on short period Earth-like planets. And it has these 4 cameras. Each camera is pointed slightly different direction, and it lets the telescope monitor an entire strip of the night sky simultaneously, almost from horizon to pole. In the field of view, it can essentially monitor hundreds of thousands of stars at any given time. Some of those stars are then pre-selected to be measured at a higher cadence than others. This is sort of dominated by how much data the telescope can download. And then every month, the telescope has this sort of the stair and step strategy, where it pivots every month to monitor a new patch of sky. So over the course of a year, it will tile the entire southern hemisphere. That's what it's doing right now. It's about 2/3 of the way through that. Then it's going to flip and do the northern hemisphere, hopefully in a few months. So luckily, this data set exists. Tess has been operating phenomenally, downloading lots and lots of data on stars all over the bright sky. It's an amazing, amazing mission. But there's one sort of drawback when it comes to finding long period planets. So this over here, this is the amount of time Tess spends on any given part of the sky. And if you look, the overwhelming majority of the sky is only monitored for about 27 days. Now, the way that Tess finds planet is they look for the planet to pass in front of the star, but you look for that signal to be repeated periodically. So if you require multiple transits to find a planet, you're sort of gonna, and you only stare for 27 days, you're only gonna find short period planets, things with periods of about 10 days or less, unless you focus on this small patch of sky. So that's great. Tess is gonna find lots of planets, but they're gonna be short period. I wanna find long period planets. So I got the crazy notion that I would look for planets that only transit once. Now this is a bit difficult because you actually don't know if you're looking at a planet or some sort of weird systematic effect. And it's gonna be a bit harder, but I think the opportunity is there to find these long period planets. And I think it's worth looking at because I think there's some interesting questions that we can answer by finding these. So I wrote a paper a while back predicting how many planets Tess was gonna find. It's always fun to make predictions. So this is a plot from a paper that I wrote. It's sort of color-coded by the type of star. People are really interested in whether planets orbit cool stars or warm stars. The circles are for the high cadence data. That would be really useful to have high cadence data. The little squares are for the low cadence data. I can work with that as well. The difference is with the high cadence data, Tess takes an image every 2 minutes. The low cadence, you only get a measurement every half an hour. Still doable. Here is our own solar system for reference. We're not really going to be finding things similar to our own solar system, but if you look, we're going to be finding lots and lots. I predict that Tess will find lots and lots of giant planets on these sort of intermediate or short period orbits, the exact sort of planets that I want to find so that I can sort of start testing some of these planet formation theories. And in my paper, I sort of predicted that Tess will find sort of about 1,000 of these events, which I think is awesome and sort of worth looking into. And if you look at the period distribution, it strongly peaked around 30-ish days. But I think there's an opportunity there to find lots of planets. Because they only transit once, Tess will throw them out, right? Tess is going to ignore them. And I think that's just sort of a missed opportunity. So I decided to go after these, and this is sort of what I work on. So for my day-to-day activities, as I go through the hundreds of thousands of light curves from Tess. So I go through Tess data, and I say, okay, Tess, you stared at this star, and what did the star do for 30 days? Okay, there it is. The star had some amount of brightness over time, so what we call a light curve. And then I'm going to go through and scan the light curves and look for one of these dips to show up, right? Now, if the dip is periodic and repeatable, Tess will find it, call it a planet. But I want to find these single dips, and then I want to sort of investigate them and look to see if they have this characteristic transit-like shape. And if so, then begin my process of follow-up. So now, Neil, I'm told that you study for these talks. You read in advance. So we're going to have a little pop quiz called Is This a Planet? So welcome to the audience. little audience participation. All right, so is this a planet? We're gonna play a little game. So here's one of the candidates that I found that my algorithm picked up. This is the actual data from Tess spanning 27 days. This is an observation every 30 minutes. And here's a zoom in. So a quick thumbs up or thumbs down. Do you think this is a planet? Not everyone can copy Neil, though. All right, we see a lot of thumbs down. OK, yeah, not a planet. This is just stellar variability. So this particular star sort of pulsates. And then right here, it just went deep enough. It triggered my algorithm. All right, we toss that out. Next up, how about this one? Yes? No?
What does the 30-minute sampling mean? Short exposures or an integration over 30?
It's actually, yeah, it's a buildup of integrations. But there's only so much bandwidth that you can download. So they prioritize certain stars to download an image every 2 minutes. Everything else gets one every half an hour. All right, so quick, thumbs up, thumbs down. All right, we've got a bit of a mix on this one. All right, this is also not a planet. So it turns out the spacecraft does some weird things every now and then. Has to keep itself stable, and it introduces these systematics. We call these momentum dumps. Sometimes they're positive, sometimes they're negative. Luckily, I wrote some software. I filter these out now. I'm done getting tricked by those. All right, how about this one? Oh, we got lots of thumbs up for this one. We still got a thumbs down. Turns out this one's also not a planet. This was actually, so this one was a very promising candidate. I was really excited about this one. So I went and I measured the properties of its light curve, but then I compared it with the actual properties of the star. Turns out this object is too big to have been caused by a planet. This was actually another star passing in front of another star.
From the shape, that looks like.
It does, yeah, they're identical. So this is one of the things, one of the more recent upgrades to my software is we now compare this with the properties of the host star. So anyways, these are the sort of things that I'm doing on a day-to-day basis. And I get to play this game all day, every day. It's really fun. But every now and then something comes along like this. So this is TOI 173. This is actually the high cadence data. So this is an image every 2 minutes. And this was actually found by the Tess team. They would have thrown this out, but I said, don't you dare, this is awesome. And I went and fitted this individual transit. So this is the single transit. It's an amazing light curve. This is exactly what I've been looking for. So I went out and measured it, and I was trying to figure out what are the properties of this planet. So the first thing you would want to do when you find a planet like this is figure out when is it going to transit again. So you can start scheduling time on telescopes to go confirm it, measure all of its properties. It's a lot of work to go confirm these things, but you need at least a starting guess at sort of when is it going to transit again. So this is the only equation I'm going to show, but this is sort of what lets me do this. So this equation says that the period of the planet, which I don't know, I want to know, is proportional to the density of the host star. And I had to work this out in my job interview. I'll do it again if necessary. And the shape of the light curve. So the duration, the sort of inclination, and the depth. If I can measure this well, this is the code that I wrote to do that, and then I can look up reconnaissance information to measure the mass, to get any information I can on the mass or the radius of the host star, then I can start to begin to put together a guess on what the actual period is. Sometimes the guesses are good, sometimes they're okay. It depends on how well we measure the light curve and how well we understand the density. But this is a distribution from my code of the period. This thing is probably 35-ish days, but it could be anywhere from 20 to 50 days. That's quite a large window. And telescope time is expensive, both in monetary time, but also in human people hours to operate them. So it would be very difficult to then go follow these up. But luckily, I built my own telescope as a graduate student. Did you have a question?
I was going to ask you, how close did your prediction come to its actual?
Well, we don't know its actual orbit yet.
You're right, you're going to get there.
Yeah. Well, hopefully, at some point. So I built a telescope as a graduate student. I operated on behalf of the Ohio State University, Vanderbilt University, and now MIT. It's a 0.5 meter, fully robotic and fully automated telescope. So I get to sleep at night. It wakes itself up, points at all the things I tell it to point at. And I've been using it for the past 3 years to measure the properties of hot Jupiters. And then I want to transition now to measuring warm Jupiters. The only difference is you get less opportunities to observe a warm Jupiter, but the durations are a little longer. So this planet, which was EPIC 24, barcode, was discovered by an MIT graduate student, Liang Yu. She recently defended her dissertation, and this was actually part of her dissertation. So I was able to participate in this. So this is a planet that she found, and I was able to re-observe it from the ground using my telescope and help constrain its properties. So this is actual data from my telescope. That's the gray points. I take observations every 30 seconds. You can then bin and average those together. That's the white data point, and you get a rough estimate of sort of the properties of the planet. So I want to do this with the warm Jupiters because I have all the time on the telescope, and I can just point and sit and stare over a week or two or more and catch the next transit of one of these single transit events, given some information that I help guess approximately when it will be. So if I can get it down to like a week or two window, I can point my telescope at it, monitor it for 2 weeks straight, and hope we catch it. So I'm really excited about this. Unfortunately, my telescope is located in Arizona, which is in the northern hemisphere. So I sort of have to wait for Tess to point to the northern hemisphere, although we're going to get some targets now. But right, yeah, so this is a 4-hour transit because it's a short period planet. We're going to be looking at sort of 10-ish hours or even longer planets. So I'm really excited about this. I'm really excited to follow them up with this telescope that I built. So very quickly, sort of what is the state of affairs right now? Where are we at right now? So these are all of the known giant planets from the NASA Exoplanet Archive. So this is the brightness of the star that the planet orbits. So these are really bright stars, 5th magnitude, so bright that you can actually see these with your eye if you have really good eyes and you're somewhere really dark. Essentially, all the stars in the night sky that you can see with your eye live above this plot. So I was being sort of trying to be funny there. No one laughed. It's OK. So everything that's on this plot, you need a telescope to look at. And the further down you go on the plot, the bigger the telescope you need. So it makes it very difficult to sort of understand the properties of these these planets down here. And then this is the period distribution. So most of the giant planets that we know about all have very, very short periods, 1 to 10 days. I sort of talked about this earlier. We don't really have very many long period planets. Specifically, we have almost no long period planets around really bright stars. All right, and that's exactly the problem that I want to solve. I want to go out and find lots and lots of planets to occupy this sort of area of the diagram. This is sort of the period distribution for what I predicted single transits will look like in Tess. For reference, this is that star that Liang found. It's sort of 11th magnitude. That's within the wheelhouse of my telescope. I'm excited about this. This means I can find or follow up anything that we can find in this area. The one good example I showed you, TOI 173, this is where it lies with the period sort of a guess. We actually don't know the period yet. We're still working on confirming it. Unfortunately, it's now behind the sun, so we have to wait a few more months before we can finish that up. And I just stepped on my cable. And here are some of the other candidates that Tess would have thrown out had I not been in the room and said, don't you dare. These are all possible single transits. We don't really know the period of these yet. These are sort of the best guess from the code that I wrote. And at the moment, I am working on sort of a catalog of sort of all of those light curves I was showing you. These are ones that I'm finding myself, and I'm hoping to have a catalog of about 100 more candidates to throw up here on this plot here within the next few months. But these are the ones that we know about so far that are publicly available. And then I'm going to, like I said, hopefully we'll have about 100 more to start filling out sort of this part of the diagram so we can sort of have this sample of giant planets that we can then go after and hopefully start answering some cool questions. In the meantime, the first single transit, at least I'm calling it a single transit, that was actually confirmed was TOI 186. This was a single transit that we identified very early in the Tess mission, but it happened to be in that camera that pointed straight up where Tess is going to look at for a year straight. So while all the work was being done, it actually transited a second and then later a third time. So it was actually confirmed by my collaborator, Diana Dragomir. It's actually the longest period planet found by Tess. So I've been telling them, single transits, long period planets, it's a good thing. So I'm really excited about that one. That's the first one confirmed so far. And I'm hoping to find lots more. So I maintain that if you want to understand planets, Earth, super Earths, whatever sort of planets you want to understand, you also need to think about these giant planets and how they formed. There's sort of this 25-year-old unsolved mystery with how do you create hot Jupiters? How do how do they affect solar system architecture, all these interesting things. But we haven't been able to understand these because there just haven't been that many long period giant planets around bright stars. I think Tess is finally going to give us those planets, and I'm really excited to go find them. Thanks. A big shout out to my collaborators, Diana Dragomir, Chelsea Huang, Hubble Fellow and Torres, respectively, and big thanks to Neil and Jane for all their support to let me do all this.
Neil.
Sorry, my question is not totally related to the subject you're looking at, other than you started off you showed most likely the two scenarios on why, if a planet was out far away, either if it's a circular orbit, why it tends to move in over time, or if it's one of the elliptical ones usually caused by another event that happened. In either case, there must be, or you must have some idea of what could cause a planet like our own Jupiter to go, perhaps that may have easily started at much closer to our sun, perhaps.
Right.
But then something caused it to not only move out, but to move out in a circular orbit.
Right, so there are...
What, my only question is there a simple explanation of what might cause a super hot Jupiter to move out?
To move out. So for a giant planet, it could move in or out, and that has to do mostly with the initial conditions of the gas clouds, which are poorly constrained because we find it very difficult to observe stars when they're embedded in this giant disk. So the initial conditions and sort of the initial conditions of the planet and the disk itself will sort of set whether or not it's possible for the planet to migrate inwards or outwards. There are predictions that in some scenarios we will have that inward migration, which could lead to a hot Jupiter. And in some scenarios you could have outward migration, which would actually have the giant planets move even further out. There isn't really an explanation. You would have to form a hot Jupiter close to the star and then have it migrate out, but there isn't a real plausible way to form a hot Jupiter in situ, where we see them now. So you could have it migrate in, but during that time scale, the disk would have evaporated, so there would be nothing left to push it back out.
So the only reason there's so many hot Jupiters that are in is only because they're closer to the star and it's easier to detect.
Right, so
if it's closer, it'll get in front of the star
right.
more often.
They're actually fairly rare. So whatever these scenarios are, it doesn't happen all the time. They are intrinsically rare. They're just the easiest to detect. That's why they were the first ones found, and this is why we know about them.
Salvo.
Can you tell me more about the relative orientation of Tess and the galactic center? Because I don't know, you said north-south, but I don't know relative to what?
It is, right, relative to the galactic center, it is north-south relative to the ecliptic of the solar system. So celestial north-south is actually off-centered, so some of the targets, some of these southern targets will be observed from the northern hemisphere, but it's the ecliptic, its north pole is the ecliptic north pole, which is a few degrees off of the celestial north pole. So it's not north-south. So right now it's observing the southern hemisphere, which includes the galactic center.
Is the galactic center one of the areas we cover most often, which I would have expected since there's more stuff there?
It is not observed, it's not prioritized any higher than any other particular field. In some cases, it's actually deprioritized because there are so many things there that the crowding becomes an issue. It turns out to have such a big field of view with a finite number of pixels. Each pixel covers a big patch of sky. And so when there's lots and lots of stars on a single pixel, it becomes difficult. So they actually sort of deprioritize the galactic center.
Julietta.
What potential is there for observing the eccentricity of these orbits, as you mentioned them?
Right, so from photometry alone, we won't be able to determine the eccentricity. So if I can find the period, that's great. But then we can start scheduling future observations. The primary mode would be with radial velocities. So measuring the reflex motion of the star, the planet pulling on the star. And that will have an eccentric or a circular shape. One of the problems with doing that with the existing sample of planets is that they're around the long-period giant planets, is they're around really faint stars, and so it becomes difficult to make that measurement. But if you can do that around brighter stars, you can actually begin to disentangle the difference or discern the difference between a circular and an eccentric orbit. All of that is going to require telescope time and resources, so we have to sort of, once I provide Tess with hundreds of candidates, which I'm going to do, then there will be a priority scheme because there's only so much RV time and RV telescopes. Not to mention all of them will be prioritized towards the actual Tess mission itself. So trying to pull some of those away to follow these up, we'll have to sort of pick and choose which ones we think, and then measure their orbits, and then get the eccentricity. So that's down the line.
Howard.
The migration, whether it's inward or outward, happens early in the lifetime of the solar
very
system.
early.
The gas cloud is still
Yes.
there. Is there any reason to believe or not believe that the solar system stays stable afterwards? It would seem to be a very germane question to life and
Right. It should stay stable. After that, it's the interactions between the planets themselves. So there are instabilities that can happen. Right. So after that,
probably a billion years for some kind of life.
right.
Or a billion years.
Yeah. So after that, it's going to be any migration that happens after the disk is gone is going to be through, it's going to be through interactions between the bodies.
How common the stability of our solar system is.
No, I mean, there's a lot of numerical simulations, integrations over time that look at stability, but unfortunately, we do not get to watch solar systems evolve over billions of years. But that's one of the good things about Tess, though, is because it's all sky, we can look at stars in a variety of different astrophysical laboratories. So you can actually look at stars of different ages and then compare architecture of an older a system around an older star versus a younger star, which is something really unique to Tess.
Over what time period do you think the migration takes place?
Right, so there are predictions. Each of the different migration mechanisms happens over different timescales from a few million years to a few 100 million years. So there are predictions for if you find giant planets around stars of different ages, which one of these mechanisms would be more viable. So that's also an option. But someone has to find them first.
Okay, let's thank Stephen again.